for invitation. And my talk will be some extracted results about link invariants in the joint work with Johannes Berger and Ingo Runkel. Johannes Berger was our PhD student. And we also studied manifold invariants, but I want just to simplify exposition, and I will concentrate on link invariants. It will be more general framed link invariants. And I would like to explain you what does it mean non-semisimple link invariant and why we call them non-semisimple. Okay? And just to start, let L be a link. So L is a link. And in general, I can think about frame link. So I have L1, L2. They are components of link. And assume we have certain isotopy invariant of a link. And then I want to ask, or we typically ask, when such invariant is strong enough. When or in what case it's strong enough. In topology, of course, we say it's strong enough if the invariant is able to distinguish many, I just write in brackets, many isotopy classes of nodes or links. So classes of links. For example, it's not something like, signature of a link we probably would not call strong enough. Right? An example of invariant which might be pretty strong is Jones polynomial or Stich-Drive invariant. Right? I mean, many people are probably not satisfied with claiming that it's strong. That's where categorification goes, right? But certainly it's interesting invariant, right? Jones invariant of a link, or more generally, Stich-Drive construction of invariants. So let me briefly remind you. So to define, in general, Stich-Drive invariant, we have some input data, right? So there is some input data. It's a ribbon category. C is a ribbon category. Ribbon category. Just, I'm sure many people are familiar, but just recall it briefly. It's a braided tensor category with duality. With duality maps, evaluation, covariation, morphisms, plus ribbon twists. And they satisfy all kind of compatibility conditions, so it's a kind of algebraic gadget that allows to construct an invariant. So what's the idea? Okay. An example of such a ribbon category, of course, the category of, for example, SL2 representations, quantum SL2 finite dimensional representations. And so what's the idea is that we take a link and we color each component. So it will be color link. So we color each link component, color each Li by some object, some Xi in category C. And then Stich-Drive construction, or more generally Stich-Drive functor, gives you a prescription how to to this data associate an invariant, an isotopy invariant of a frame link. In particular, for Jones, each link component I color by fundamental representation of quantum C2. Right? There are colored Jones. We can color higher weight representations of EQSM2. It will be what's known as colored Jones polynomial. Okay, this is the idea. So we have a gadget. We take objects from this ribbon category, and we color link components. And restricted construction uses a way to do the calculation. I mean, I just remind you some idea. So imagine you have some link, many components, right? You choose a selected preferred component you like. It doesn't matter which one. So I assume it's colored by object xi. And at some point, it doesn't matter which point, we cut open. So we go from link to one tangle. So we have this is my link. This is my component. And at this point I cut, and then I open it, right? So it gives me one tangle from xi to xi. And applying Christian Pori functor, or looking at this diagram as a string diagram in my ribbon category, right? I interpret it, or I actually calculate it, as endomorphism of my object xi in the category C. So it's some endomorphism of object xi. Okay? And let me call it. Let me call this. This is my link L, and this is some endomorphism I construct out of this link L. It's not isotopy class yet. And then to construct isotopy invariant, we calculate categorical trace, right? So I calculate categorical trace. I denote it this way, quantum trace. This uses duality maps. So I calculate this FL, and it gives me a number. And this number is isotopy invariant, right? Or in terms of pictures, I have my endomorphism, and I use evaluation correlation maps to close it. Okay?
Does the definition of ribbon category imply that the traces are non-zero and that the category is semi-simple?
I would say I don't need that it's semi-simple. And in my case, also for the tensor categories, I'm looking at tensor unit is required to be simple. So I have duality, and tensor unit is simple. So this you can interpret as endomorphism of tensor unit. Right? It's a morphism from 1 to 1, certain morphism that factors through xi tensor xi. Right? Xi tensor xi dual tensor xi. If category is semi-simple, it is non-zero. But if category is not semi-simple, it might be zero, and it will be zero in many cases. Yeah, I will say about this more for non-semi-simple category. Okay, right. So in topology again, we are interested in invariants from the point of view how strong they are, in the sense how many isotopy classes of nodes they can separate. But as a representation theorist, I would propose the following point of view on invariants to be strong. So from the algebra point of view, I want to ask the following: is invariant L? So I take L, any link you like, colored by objects. So I associate to each component objects of your favorite ribbon category. And is it able to distinguish non-split extensions? For example, in particular, this is what I'm asking. Because first of all, I keep in mind that category C is non-simple, where I ask these questions. In particular, it assumes that, for example, simple objects have some simple objects have non-split extensions. I'm asking if you call it invariant, I don't know, you give me any procedure, and I would call it algebraically strong if it's capable to distinguish non-split extensions. For example, maybe take a node for simplicity, invariant of a node and colored with some object x. Is the invariant able to distinguish x? Let's assume x is a non-split extension of two objects A and B. X is non-split. Is it able to distinguish x from a direct sum of A plus B? This kind of question, okay? So it's, in a sense,
Is it for all nodes or is it
any node. I mean, try to. I mean, if there is at least one node, it's able to distinguish non-split extensions. I call it strong, algebraically strong.
So just to be clear, so now you treat your invariant of L as just a tool to distinguish between.
Yes, I'm going opposite in a sense.
Yeah, okay.
I'm going opposite because usually, typically in topology, we like to use algebra to apply in topology. I'm asking in a sense opposite direction, opposite questions. Is topology useful for algebra? So I'm working with non-semisimple categories. So I have continuously many extensions, and I would like to see is the invariant able to detect them. And I'm claiming you for second right invariant is weak algebraically, even if you work with non-semisimple categories. Let me write a statement. So, proposition, which was known. I think for rest it's probably known. I just could not locate it in the literature. And in this paper, we proved much stronger statements. And so the corollary is this: C is any ribbon category. Is a ribbon category. Then a Stick-and-Drive invariant. Let me call it a Stick-and-Drive invariant of link L with any objects x1, xn. Depends only on Grothendieck class of xi's. Only on Grothendieck.
And this is split Grothendieck group.
Yeah. I mean, right. For me, is what usual Grothendieck group, right? You take, for example, in Grothendieck group, x equals a plus b for any non-split extensions. Okay. And so, Stick-and-Drive invariant actually, I mean, whatever link you take, if C is
the usual this is the usual Grothendieck group of an abelian category.
Yes. So, Stick-and-Drive invariant depends only on Grothendieck classes of xi. So, in a sense, it's all right. It's just a function of x1, class of x1, xn. So in particular, it's not able to distinguish non-split extensions, and so algebraically, it's a weak invariant. Okay. Let me try to maybe explain another way this statement. It's related to the properties of the categorical trace. As I mentioned here, the main ingredient of Stick-and-Drive construction is a categorical trace. And there is interesting property of categorical trace, that categorical trace on every proper tensor ideal of C is identically 0. And let me now, to explain this, let me now go to, I want to review you certain statements and properties of tensor ideals. Start. What I call tensor ideal. So I need to spend a few minutes on tensor ideals. This is even more general. This is a statement for any C just needs to be pivotal. I don't need even rating, just pivotal category. With simple tensor. Okay, tensor ideals. Okay, so what is tensor ideal? Tensor ideal may be I in C. It's a full subcategory. closed under attracts. Closed under attracts. In particular, if X is in ideal and X is of the form A plus B, then each A and B are in the ideal. So if X is in ideal, then A and B are both in the ideal I. And closed under tensor products, right? If X is in I, then X tensor A is also in I for any A in C, for any A in C. So this is what we call, this would be a right tensor ideal. Okay, and when I'm not talking about braided case, like pivotal categories, I always mean right tensor ideal. Okay, maybe I give you also just some examples of, simply we can define left ideals and two-sided tensor ideals. Okay, maybe some examples. So there are trivial examples. I is just 0, or I is the whole category C. These are trivial examples. The other important example, I is a subcategory of projective objects. So a takeful subcategory of projective objects in C. So why it is an ideal? So this is related to the property that, so assume P is projective, and I take some object V, I multiply with object V, any object in C, right? I want to show that this is projective, and for this I want to analyze this home functor, right? If I show that this functor is exact, P tensor V is projective, right? But because of duality, this is isomorphic to home.
Can I ask you something before we go further? Just, I'm just a little bit worried about the statement about the Rifstichen-Turaev invariant, because it seems to me that it takes into account even smaller, even less information than the Grothendieck group, because quantum dimensions of certain simple modules are equal.
Yeah.
You know, like if you basically it takes into account only the first alcove, and that's less than the Grothendieck group, which is the first.
Yeah. I mean,
So if,
some objects could be projective and it's just 0 if at least one component is colored.
but I mean, it's not one-to-one with the simple modules. If you just take simple modules, for certain simple modules, you will get quantum dimensions that are opposite to each other, and so you will just get.
But it doesn't contradict.
The first alcove of highest weights generates the whole thing.
It doesn't contradict to what I said.
No. You just yeah. So
I just say that it's
Grothendieck group, but even less than that.
Sure.
A quotient of it.
Sure.
Okay.
So, I mean, okay, easy way to see that why projective objects form an ideal, because of duality. So this is iso to home P argument tensor with dual of V. And now this is a composition of exact functors, right? Okay, I say the category is rigid with duality, left and right duality. This implies that tensor product is exact, so it's exact by functor. And so it's tensoring, so what is this functor? It's tensoring first with some object, which is exact functor, and then composed with home P to anything. So it's a composition of two exact functors, which means it's exact. That's why P tensor V is in the ideal. That P tensor V is also projective for any V. Okay, I will give you for algebraically strong, to define algebraically strong invariant, I will need more sophisticated tensor ideals. I will discuss them maybe, I think I will discuss them a bit later. Let me just now, I can explain you why trace, right, I can explain you why trace is 0 on every. So this is a statement, at least, what I'm saying. I define you what is a right tensor ideal, and for any pivotal category, categorical trace of any endomorphism of every object, of any object in a proper ideal is 0. So if you want trace, doesn't see any ideal.
Sorry, can I ask a question? Do you need that the tensor product? Do you always assume the tensor product is exact? This follows from.
It follows from rigidity.
Okay.
Category is rigid. Yeah, otherwise many things cannot work. So here tensor product is exact. Right, what is trace? Again, trace is categorical trace of some endomorphism of some object X. As I was explaining here, it's composition of, I read diagram from bottom to top. I start with tensor unit. I set my tensor unit into xi tensor xi dual. Right? Then I apply endomorphism of xi, and then I use another evaluation map, and I'm back to the tensor unit, right? So this composition map should give you a number, and assume this number is non-zero for x in some ideal, in any ideal, any proper ideal. So if it's not zero, so assume it's not zero, this composition I can normalize such that tensor unit is retract of xi tensor xi dual, right? And because xi, or maybe now I can erase just I. So by assumption x was in ideal, x tensor x dual is also in ideal, right? But 1, if it's non-zero, tensor unit, because I mean this is map, and if I normalize properly, it's a section of that map. So 1 is a retract of x tensor x dual, which is object in an ideal. An ideal is closed under retracts. So that means that tensor unit is in ideal I, but tensor unit generates the whole category C. So if a tensor unit is in ideal, that means that ideal is the whole category C. So, so on the proper ideal, trace is always 0.
So does this first conversely, so if you take all objects for which the categorical trace is actually 0, does it give you?
So again, if you take what?
If you take
all objects
for which the categorical trace of the identity is 0, does it give you?
I think you're saying this. Okay, actually, you can define another thing, an annihilator of trace. I define such that all objects x and c, such that categorical trace of any endomorphism of x is 0. So it's not hard to show that this is a tensor ideal, and it's the biggest actually tensor ideal you can prove. So what happens is that, so we have category C. I just explained some, so we saw projective. And okay, the statement, not going to write, I will just say it in words, that projective ideal, this one I described here, it's the most fundamental in the following sense. It's smallest tensor ideal. It contains no proper subideals. It's easy to show because the projective ideal, we can show that is generated by any projective object. Like any projective object, it generates the whole. And so it's smallest tensor ideal. And also you can show that it's contained in any other tensor ideal. I mean, you might have many, actually. Typically, we have continuously many tensor ideals. So you can show that projective ideal is always contained in every other tensor ideal. And every other tensor ideal will be contained in this annihilator of categorical trace. And it's a proper subideal in C. Okay. So this is the structure. And so these guys in between, I will call them intermediate ideals. And they will be the source of strong, algebraically strong link invariants. This is why I want to explain to you, at least in a very simple example. Example comes from exterior algebra. You cannot imagine a simpler non-semisimple example. Okay, but before giving an example, From this property of categorical trace, we see that categorical trace cannot do the work, right? Because it sees essentially only semi-simple part. It's zero identically on every ideal. And to discuss this non-semi-simple invariance, I need to review. So the idea is old. It goes back to Turaev, Gir, and Petitot-Miron, that indeed categorical trace is often zero on every tensor ideal. But then we are asking, maybe these tensor ideals, they have their own trace. Just there is another trace on them. So the idea is to define another trace which does the same job as a categorical trace. So I think a name would be trace on the ideal, but by historical reason it was called modified trace. Or I will not use often modified, just trace on ideal. Trace on an ideal I. So what is this? So it's a linear function. It's a family of linear maps from endomorphism of each object X into your ground field and over all objects in your ideal. Okay? And such that two important properties satisfy. First of all, cyclicity. P, F, G. So assume Fp, Q, two objects in my ideal, and I have one map G and F. So it's just cyclicity property. So composition, right? So this is something you ask for trace, right? But now, in order to be able to apply to link invariants, one need a special property called partial trace condition. Partial trace. Or in a sense, it's a property that tells you that this modified trace respects your monoidal structure. Or partial trace, what's partial trace? Let me write it graphically. So if I have my right ideal, and I call it will be again for right ideal, maybe right trace and so on. So assume you have a morphism from P tensor V to itself. So for every endomorphism of P tensor V, it should be such that T on P. So as I say, this is so P is my ideal, right? So for every P in ideal, and every B in any object in category C, and for every morphism and the morphism, this should be modified trace on P. And here I use my pivotal structure. So I use evaluation, correlation maps. So if you want, I just close one line. Close every line on the right. But I should always keep one, which corresponds to the object in the ideal. So I can evaluate it. So these two things should be equal. That's a partial trace condition. Maybe some statements about in particular we have multiplicativity. For example, if you evaluate T P tensor V of the form F tensor G, right? If your morphism splits, the result of multiplicativity, it will be T P of F, and because it splits, you have categorical trace. So here it will be just categorical trace C on V of G. So yeah. In categorical trace, you would have multiplicativity. You would have everywhere categorical trace. Here it's picked out as a scalar. Yeah.
Okay, so for such product, then T on if you take two objects and the trace and if you take two objects in your ideal, then the categorical trace is 0.
Categorical trace, you're right. But for this kind of morphism,
Okay, but not for all.
or in the ideal, this is 0. Right. But there are many morphisms which are not split, like braiding, for example. Okay. And to find such traces is maybe I will give you some properties. So if ideal I is a whole category C, there is a unique solution of two scalars. Modified trace T is categorical trace of C. Second maybe example. Interesting ideal I is a projective object. Let's see. Then there is a long history of. So I think I should also of course mention. I say it briefly, but I should mention people. So the idea is to introducing trace. It came from the work of Turaev around 2010. Turaev, Gear, and I just write abbreviation Patiromiran. They developed the idea of modified dimensions. Okay. And then around 2011, 2012, also Gear, Patiromiran with Kujava, and independently with Viralizier. They developed this theory of modified traces, and they constructed many examples. For example, I think it was around 2012. So T on projective ideal is unique and non-zero. Is unique and non-zero. I think the first result was around 2012. If I has a simple object. And in this case, they give an explicit construction of such a trace. But this assumption was important. Then
This is for pivotal categories. You don't need a ribbon structure.
for pivotal categories, you just need that you have the duality. And pivotal structure, it's isomorphism between two factors, identity and double dual. And it's monoidal isomorphism.
Spherical category.
For example, spherical category, yes, spherical category is stronger, right? Spherical category means left trace equals to the right trace. So in pivotal category, you have two traces. You can define notion of traces. You have left and right trace. In spherical categories, they are equal. In particular, ribbon category is spherical, and spherical is good.
So you don't even need spherical, but you need some pivotality, and your left dual is equal to the right dual.
Right. In order to talk about even this, right? Pivotal. Okay, it's erased. Pivotal. Yeah, pivotal category means I have pivotal delta. You can think about it as monoidal isomorphism between double dual functor. For example, right duality, or you can rephrase it that as isomorphism between left and right dual. Okay, and this trace on tensor ideals, it has a long story. So as I say, it started with 2010, and then there was some partial results. Yeah, then there was a work of myself, and 2007, my work with Ingo Runkel. Got interested into the subject, and we proved existence and uniqueness of modified trace on projective ideal for every factorizable category. C if C is factorizable. Factorizable means that double braiding is non-degenerate in a certain sense. And then with with Christian Blanchard and Belakova in 2018, we proved that in the case if C is a category of representations of a Hopf algebra, H is unimodular Hopf algebra, and I looked at it ideal projective objects for unimodular Hopf algebra, finite dimensional unimodular Hopf algebra. We proved that on that ideal or projective objects, modified trace exists in unique and non-degenerate. And then later, this was generalized to, I mean, it's the same year, but let's say almost a year later, it was generalized for every unimodular category. So if you take C pivotal category, if it's unimodular, what unimodular means? Unimodular means projective cover of tensor unit. You take a dual, it's iso to itself. Or in terms of Hopf algebras, it means that the integral of the Hopf algebra is two-sided. Or saying differently, the circle of projective cover of tensor unit is a tensor unit. This means unimodular, and so for unimodular category, we have this finally fundamental result after all these years that this fundamental ideal has a unique non-degenerate modified trace, and this trace can be used to okay, maybe before going to more complicated, let me just give you an idea of this topological trace.
Sorry, what's the relation between these generalizations, like the factorizable and unimodular Hopf algebra, and the existence of a simple object? Are those different, or is it one?
Yeah, factorizable implies this, and factorizable also implies this.
Okay.
So this is if you have braiding, yeah, okay. I mean, there are some intersection between them, right? So here you might not need even a braiding. Right? It's a simple object. Here I need, of course, braiding, but even not degenerate. But what we actually proved that every factorizable category has necessarily at least one simple projective object. This comes from non-degeneracy of the braiding. That factorizable implies unimodular. It's all the results. Right. So this case is the most generic. So application to link invariants. So what the idea that the idea that I take a link, or I mean, in general it might be ribbon graphs, but okay, I take some link. All components can be colored as you like, but you ask at least that at least one component is colored by X from your ideal. So not every coloring is allowable, but is allowed. But at least one component should be colored with object from ideal, because this is where you use this trace, right? And then I do cut open. So again, I got this, and actually it's same as there. I have some link. I have my component. I cut it open. So I get this endomorphism of X, where X is an ideal. And then I pass. So let me call this again FL. And then what I pass, I just evaluate T on X of this FL. Right, and you get a number. So this is a theorem of Gir, Potiromiran, Tura. I mean, okay, again, it was developed in these several works over several years. So the theorem, due to these people, let me call, I mean, it's standard notation. Okay, let me call this maybe, I don't know. This is, I will denote invariant, depending on ideal, and depending on the modified trace of this tangle, FL, of L, which I define as Tx of L, that this is a well-defined isotopy invariant of L. I mean, I say link in this case because it's ribbon, it's friendly. It's isotopy invariant of a friendly. So in particular, this is quite non-trivial property where this partial trace condition is responsible that because you might have several components colored by object in ideal, and what they say, it doesn't matter which one you choose and where you cut. It will be all the time same number. Okay, now I should go to the main class of ideals. So this is about modified trace, and so I mean, okay, with this property you see, right, that indeed one should look at ideals and ask whether ideal has a trace. Not every ideal has a trace. So here is an example of projective ideal when it has trace. It has trace only in unimodular case.
To come back on that, do you have a way to actually normalize it? So when it's unique on projective, it's unique up to a scalar, I guess, on your second example. For if I is a ideal of projective
Yes.
object, say you have results saying it's unique, but it's unique up to.
Yeah, up to scalar.
And do you have a way to actually kind of normalize this?
Yes. Yes.
Okay, you can.
No, but the base is okay. No, maybe I'll say it. Okay. I mean, really, typically, okay. What you can prove, so what you can always prove that. Okay, so T. What was it? Take projective cover of 1, and right. I have a canonical projection of. I have canonical projection of my projective cover of 1 into the tensor unit. Phi1, and then I composed with some embedding of the tensor unit into Phi1, right? And what you can prove that this is always non-zero. It's not true that modified trace on identity on projective cover of tensor unit is not zero. There are cases when it's zero, but this is always non-zero. And okay, I wanted to say you can normalize it this way that it's 1, but so this is canonical, but this is this is not canonical. No, I don't. I mean, there's no. I think there's no proper way to. Okay. Organizative invariant. I can erase the definition. Maybe one last remark that it's not just a result about existence, but there are explicit formulas, which are very crucial for the work I'm explaining. So in this case, with Belyakova and Blanchet, myself, so we it's not only that we proved existence and uniqueness up to scalar of this trace on projective ideal for a Hopf algebra, but we give explicit formula of this modified trace as integral of Hopf algebra H. So it's not exactly integral, but something very close. Okay, so this is typically, if you work with some Hopf algebras, semi-simple Hopf algebras, this is fundamental thing you want to calculate, integral of Hopf algebra. And actually, modified trace is deeply connected to the integral. And this is, for examples I'm going to explain, this is the main tool of calculations. So we can actually explicitly calculate these invariants. So let me give you examples. So as I said, not every tensor ideal has modified trace. So it took quite a bunch of years to just understand the fundamental tensor ideal projective objects. But there are many more other interesting ideals. So let me mention this, what I call pullback ideals. So in general, the idea is simple. So pullback ideals along some functor f, and let's assume I have two categories C and D, and it's a pivotal functor. So it's a monoidal functor which respects pivotal structure. Right? And assume I have ideal D in my category D, and what I call a pullback ideal. So ideal, how do I denote it? Let me write it. Ideal F star is all objects X in C such that F of X is in ideal of D. Okay. So we can prove that this is a tensor ideal in C. Tensor ideal in C. What is interesting for this is that if you have a Hopf algebra and you have a Hopf subalgebra B, we have such a functor. I mean, assume B shares same pivotal element as H. So you have such a functor F. It's just restriction functor. It's just restriction. B mod. And on this side, I take projectives of B mod. Right? And then you can ask, what is a pullback ideal? It will be huge. Actually, no, it depends on how B is small, but if B is not completely H, the pullback ideal for restriction functors is quite big, might be quite big. Of course, it contains projective ideal of H, but it's much bigger. And maybe I will give you an example of this. Maybe I finish with a statement about. No, first I give you an example. So let's take exterior algebra. So let's take B. I will use even dimensional vector spaces. It's needed for unimodularity condition for existence of modified phrase. Okay. So, and I take exterior algebra of this vector space. This I call S. I'll call it Sn. Okay, so exterior algebra. And about exterior algebra, you can think as Hopf algebra in S vect. Hopf algebra in S vect. So in category of supervector spaces, right? It is a commutative and co-commutative Hopf algebra. Commutative and co-commutative. So for example, for element V in V, coproduct is V tensor 1 plus 1 tensor V, but it should be taken with respect to the gradient, right? So. And typically we think, Hopf algebras are, maybe I will also introduce you ribbon structure on this Hopf algebra. So because it's commutative, of course, it has a trivial ribbon structure coming from S vect. So, the category of representations, let me write my category C will be Sn mod. The category of representations, it has a ribbon structure just from S vect, it's just symmetric category, so it admits this trivial ribbon structure. But actually it admits another interesting ribbon structure, maybe not so well known. It admits a ribbon structure, so it makes it supermodular. Supermodular in the sense that the Miguel center of the category is just S vect. So let me choose a basis here. Fi plus minus, I from 1 to n. And let me introduce a copairing C, sum over I, Fi plus tensor Fi minus, minus Fi minus tensor Fi plus. Okay, that's this element. And then the statement is that you can define our matrix, it's just exponent of C. This gives you our matrix. So this is not a genuine copairing. And this gives you our matrix for this Hopf algebra. And with respect to this our matrix. And ribbon element will be also exponent of multiplication applied to C. Okay. So this data makes this category supermodular, in the sense that the only transparent object is tensor unit and its fermionic version. So double braiding is almost not degenerate. So this is my example where I'm going to test these invariants with the multiple trace. And let me give you an example of the pullback ideal. So of course, for the pullback ideal, I can take, first of all, I can take W, any subspace in V. And it defines me Hopf subalgebra, right? Right, it defines me, I don't know, T, right, exterior W, it's a exterior on V. It's a Hopf subalgebra. Hopf subalgebra. And now I'm interested in the ideal of objects such that under restriction or under this Hopf subalgebra they are projective. So as I said, objects which are projective under any Hopf subalgebra gives you tensor ideal. Let me give you an example when n is 2. And I consider, so which means that V is 4. And I consider subspace W of dimension 2. So I consider C square inside C4. So I choose here a basis, for example, F1 plus minus. Okay? Just first half of the basis elements in V. And what are objects which are projective? So essentially the ideal, so I can say, let me describe the ideal of this restriction functor, restriction from exterior algebra of 4-dimensional vector space to 2-dimensional vector space. So the typical objects in this ideal, they are 4-dimensional. So let me start with notations of, this is tensor unit. It's a bosonic, it's bosonic 1-dimensional vector space. There are fermionic spaces. Right. And I'm going to describe you now a structure of projective cover of tensor unit for the Hopf subalgebra based on 2-dimensional vector space. Right? This you know very well. It's just Grassmann algebra with two generators, right? So here is the action of F1 plus, here is the action of F1 minus, here is the action of F1 minus, and here is the action of F1 plus. What I wrote you is a quotient structure, right? It means that there is a trivial submodule. If you quotient, there are two fermionic 1-dimensional representations. If you quotient, you get back also extra boson. So it's 4-dimensional. They're projective over this Hopf subalgebra. And to describe this ideal, essentially, if you want, I'm asking in how many ways I can lift this object to the bigger subalgebra action. So by definition, it will be in this ideal, because if I'm able to lift it to an object over this algebra, it is my ideal. And indeed, you can find, you can prove that how many lifts you have. So you can act with F2. So maybe I will write it. So I will not write explicit generators, but the other pair of generators, it can act with some complex numbers: mu1, mu2, mu3, mu4. So I have 4 complex numbers, and they are all. So, and I'm going to make a matrix mu1, mu2, mu3, mu4. And I call these objects P mu. P mu. So I have it's a 2 times 2 matrix with this complex entries. And P mu is iso to P mu prime. Has a module over the big exterior algebra if and only if mu is equal to m mu prime. So it's okay. So we have so many lifts, and so in particular in this tensor ideal, of course, they contain projective objects, but they're here. I mean, they're 16-dimensional. But the typical object, they are this 4-dimensional, and they parameterized by matrices 2 times 2. So this is an example of non-trivial tensor ideal, and maybe I should make also a statement for modified trace, right? I just gave you an example of intermediate tensor ideal. What about modified trace on this ideal? And in the case of Hopf algebras, okay, actually it's about this pullback ideals. Okay, this is a theorem of myself with Fontalvo-Orozco. I think also around 2018. So we were looking at this construction, and so if, okay, let me formulate it in this Hopf algebra case. If B is unimodular, so if it's unimodular Hopf subalgebra, then T on this pullback ideal exists and non-zero. I don't claim anything about uniqueness. This I don't know. It might be even degenerate, but it's certainly non-zero. And we give explicit formula in terms of the integrals. Okay, so we can actually calculate such a modified trace. And now let me give you a table of. I think I presented my ribbon categories. It's very. I think it's very tricky. So yeah, let me give you an example of for torus nodes. Torus nodes. 2m. So I will use notation so T over mx. So I take 2m plus 1 braidings. Sorry, m is odd number, right? Here's m. M is just odd number, and I close it, right? So this is a notation for TMX. Now I'll write you a table for invariants of such a torus nodes for different ideals. So here I'll write ideals in C. So there will be this SN mode, and maybe I don't have enough space. I think it's enough to. So here will be ideals in C, and here I will write you invariant. This how I denote it, invariant using the modified trace, depending on the ideal and T of this TMX. And X is object coloring. So we'll have 3 cases. So SN mode for whatever n, and of course the trace is just categorical trace, right? In this case, as I said you. And from the very beginning, I said that it does matter. I mean, I don't need to color it by non-semisimple objects. Because it only depends on Grothendieck class. So it's enough to color just by X is just C10, X plus, and X minus is C01. Just 2 simple objects. So my category has only 2 simple objects. Right? And the invariant will be, the corresponding invariant will be just a sign plus minus 1. Right? And there is no difference if you would use this category of just a select. Same. Right, projectives of Sn and the trace I have. So then invariant for projective cover of 1, let me just take X to be projective cover of 1, invariant is m to the n. M to the n. And now for this for n equal 2, I will write the invariance for this so ideal is this, the one I described here. Right? So as object, I take this p mu, and mu is this matrix 2 times 2. Right? And the invariant in this case is 2m, 1 plus determinant mu. So what do we see? First of all, for example, first of all, this invariant detects mu, not all mu i's, because mu i's, if you want, they are coordinating extension groups. See, because this number mu, it tells you what extension between this simple and this simple it takes. So I would like in general to find maybe nodes or links that are able to detect all mu i's. Here I give you an example, it detects a combination of mu i's, but it detects. For example, if it would be split, that would be 0. One thing, another thing, for n equal 2, this particular case, n equal 2, you see, projective ideal is not detecting difference between torus node and its mirror image. Mirror image m2 minus m for n equal 2. And this intermediate ideal for n equal 2, it detects. So on one side, intermediate ideals are interesting, may be interesting for topology, at least it detects more isotopic classes than projective ideal. And it also detects extensions. That's why I think, this I will finish with this, that's why these invariants based on modified trace deserve to be called non-semisimple.
Because we have a reception immediately coming up, maybe we can ask 1 or 2 quick questions for the speaker and save the rest of the questions for the reception.
We don't have to be on time necessarily,
okay.
so yeah, go ahead and ask a question.
Yeah.
I have a question to the right-hand side of both, to the ribbon elements.
Yeah.
Could you give an intuition how it will look like in this kind of low-dimensional exterior algebras below? Yeah, what it would evaluate to in terms of the basis as you have.
Yes. Yeah, it's actually quite simple.
Can I ask a question about the same? So is it R that is exponent of C? Is it R1 times R21?
No. It is R. It is actually R.
And so, in this example of SN mod, do you understand what's the biggest ideal?
Projective. Biggest ideal. No. This would be interesting. I think one should look at biggest ideal, which is an annihilator of categorical trace, which essentially contains all non-semisimple objects.
Yeah.
Right? And to find kind of trace, I think it might be some twisted version of a trace. And then it should detect all extensions, I think. I would expect, but.
So, sorry. So do you expect that all then traces on smaller ideals would be a restriction of?
No.
Do you think there's more room?
For example, in these examples, I cannot prove in general, but in this example, modified trace on this ideal, you see it's non-zero, of course, but what happens if you take projective object? It's identically 0 on projective ideal. So this trace on this intermediate ideal is degenerate. It doesn't see projective ideal. So if you want restriction, the projective ideal is 0.
I just wanted to ask you about the case of the quantum groups at roots of unity, where with the algebra of divided powers, we have a braided category and everything, and the projective modules have a simple object that is well known, the Steinberg module. And so in this case, is there a simple expression for the modified trace for the projective ideal? Is it somehow related to the character of the Steinberg module? Can you say just something about it? Or?
It is related to...
It's computed anyway. There's a
But as I say, with Christian and with Anna, we did it for general unimodular of algebras, these quantum groups in particular unimodular. We have expression in terms of integral.
But
then you can calculate this integral for...
this is an infinite dimensional algebra. What
okay, no. For in this case, we don't... No, in this case, we don't have formula, but one can construct modified trace in this infinite case, again via idea of pullback, because these algebras, they have sub-algebras which are small quantum groups, right? So we can take a restriction, and you have what is the pullback ideal of projectives for small quantum group? It will be just projective for divided powers, same. And then you can apply pullback formula, I mean, I did say, but... So one can use actually integral of small quantum group, calculate modified trace for algebra with divided powers.
All right, if there are no further questions, let's thank Azad again.